So in this video we'll be looking at Pascal's triangle and how that applies to our combinations problems, and also kind of how it applies to something that we see in a more algebraic setting as well. And so first of all, let's start looking at what is Pascal's triangle. Well, basically it's a geometric number pattern where we are doing exactly what it sounds like. We're generating a triangle. And so we start off at a 1 at the top, and then we put 1s on each side, and then for the entries in the middle, they will be the sum of the entries that are diagonally above it. And so on our first row, we start off with a 1. Well, the 0th row, we start off with a 1. On the first row, we have 1s on the outside and nothing else in the middle. For the second row, we have 1s on the outside, and then we have the 1 plus 1 from the two diagonally above it to give us a 2 in the middle. For the next row, 1 on the outside, 1 on the outside. 1 plus 2 is going to give us a value of 3 on that row. 2 plus 1 is going to give you a value of 3 on this row. And so we can kind of generate this pattern in kind of a nice way, and it's got some interesting properties to it. And so it's actually got 3 different areas that we'll be looking at in this video. We have Pascal's triangle itself, how you generate it, which is what you've just seen. Then we've got one application to algebra where it comes to multiplying polynomials, or really in particular taking polynomials to powers. And finally, how it applies to what we are doing in probability and statistics, how it applies to the combination formulas of taking k things from n things. So we'll begin by looking at polynomial multiplication. Now, if we just got something like x plus 1 raised to the first power, well, that just gives us x plus 1. But if we've got x plus 1 to the second power, well, now we're going to have the quantity x plus 1 times the quantity x plus 1, which means we use the distributive property on it. And so we have x squared plus x plus 1 when we do that. Well, combining our like terms gives us x squared plus 2x plus 1. If we kind of raise x plus 1 to the third power, well, we can use the work that we've already done and see that x plus 1 to the third power as x plus 1 squared times the quantity x plus 1. Well, we already know what x plus 1 squared is. It's x squared plus 2x plus 1. And so we're multiplying that by x plus 1. Well, using our distributive property, the quantity x plus 1 gets multiplied by each one of those 3 terms. And we use the distributive property again to distribute across each one of the x plus 1 terms. And so when we combine like terms for a final answer, we're getting something like x cubed plus 3x squared plus 3x plus 1. So if we kind of do that for one more time, if we take a look at the quantity x plus 1 raised to the 4th power, again we're using the work that we did before. We've got our x cubed plus 3x squared plus 3x plus 1 times our quantity x plus 1. Well, we use distribution to distribute the quantity x plus 1. Then we use distribution again on each one of those terms. And then as our final step, we're combining like terms to give us a final answer of x to the 4th plus 4x cubed plus 6x squared plus 4x plus 1. Now is where we start kind of making the connection with Pascal's triangle, that probably maybe some of those numbers that were popping up as coefficients were ones that maybe you recognize when you write out several rows of Pascal's triangle. So if we just have 1, well, that's our 1 to the... That's all we have is 1 at the top. Our x plus 1 gave us x plus 1. Our x plus 1 squared gave us x squared plus 2x plus 1. Our x plus 1 cubed gave us x cubed plus 3x squared plus 3x plus 1. And so kind of what we've got drawing in here will be how we're putting those so that each one on the next row looks like the sum of the 2 diagonal terms that are above it. And so even all the way down to our x plus 1 to the 4th, we're getting the same numbers that are appearing from our Pascal's triangle. And so what we're encountering is Pascal's triangle really being related to polynomial multiplication by something called the Binomial Theorem. Now, what is that kind of fancy name? Well, it's a way of raising polynomials to powers without actually having to multiply everything out. So how the binomial theorem works is like this. Let's suppose that we want to multiply out something like x plus y raised to the 5th power. Well, we're going to start by writing out all of the rows of Pascal's triangle down to the 5th row. So at the very top, we've got our 0th row, so that's where we're going to start. Then we've got our row 1, 1, our row 1, 2, 1, and remember the 2 is coming from the 2 diagonal elements, the sum of the 2 diagonal elements that are above. Then we do that same thing for the next row, 1, 3, 3, 1. Then for the next row, 1, 4, 6, 4, 1. And finally down for the 5th row, we've got our 1, 5, 10, 10, 5, and 1. So that's where we're stopping because the second number matches the power that we're actually using there. So we're taking things to the 5th power. So we're looking at our second number in our row is going to match that power. That's how we know we're on our 5th row. Okay. Then for the next step, directly under that, we're going to write out all of the powers decreasing for the first term in our inside the parentheses. So inside the parentheses, our first term is going to be x. So we're going to start off with x to the 5th power over here on the left and just decrease those powers all the way down to 1. So we've got x to the 5th, x to the 4th, x to the 3rd, x squared, x, and 1. Then we do the same thing for the second term in our binomial on inside of those parentheses, but instead of decreasing the powers, we're going to increase the powers. So now we start at 1 on the left, so we've got 1y, y squared, y cubed, y to the 4th, and y to the 5th. So those are all increasing powers of y. And so this kind of gives us this little grid of our coefficients, our top, so 1, 5, 10, 10, 5, 1. Our powers of x, x to the 5th, 4th, 3rd, 2nd, 1st, and 1. Our powers of y, increasing 1, 1, y squared, y cubed, y 4th, y to the 5th. So the idea is that we multiply the entries in those columns. So for the first column, we'll have 1 times x to the 5th times 1, which is just x to the 5th. For the second column, we'll have 5 times x to the 4th times y, so just 5x to the 4th y for the second column. For the third column, 10 times x cubed times y squared, so we get 10x cubed y squared, and so on for multiplying the entries in a particular column. And then really for our final answer, we're just adding all of those results together. So we're just putting them together with plus signs, essentially, so that we have as our final answer x to the 5th plus 5x to the 4th y plus 10x to the x cubed y squared plus 10x squared y cubed plus 5xy to the 4th plus y to the 5th. Now suppose that we wanted to do a more complicated example, that we wanted to do something like multiplying the quantity 3x plus 4 raised to the 4th power. Okay, so our power is 4, so in Pascal's triangle we want to go all the way down to the 4th row. So we've got 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and then 1, 4, 6, 4, 1. So our second number is 4, and that matches the power that we've got, so we know we're on our 4th row. Then below that we'll have the first term in our parentheses, and we want to write those things with decreasing powers as we move from left to right. So we've got our 3x, both of those to the 4th power, 3x to the 3rd power, 3x raised to the 2nd power, 3x raised to the 1st power, and then just 1. Then we do the same thing for the 4s. but we are increasing the powers as we move from left to right. So we've got 1, 4, 4 squared, 4 cubed, and 4 to the 4th power. So again, taking each one of those, that last kind of last three rows that we put on there, so we've got our coefficients, our 1, 4, 6, 4, 1. Then we've got our powers of the 3x decreasing as we move from left to right. So our 3x to the 4th, well, 3 to the 4th power gives us 81, and then x to the 4th. Then we've got 3x to the 3rd power. Well, 3 to the 3rd power gives us 27. So we've got 27x cubed, 9x squared, 3x, and 1. Then for our powers of 4, we've got our 1 all the way over to the left. Now our powers of 4 increase, so 1, 4 to the 1st power, 4 to the 2nd power gives us 16, 4 to the 3rd gives us 64, and 4 to the 4th gives us 256. So we multiply each one of those columns, each one of those entries in the columns together to give us 81x to the 4th. 4 times 27 times 4 gives us 432 x cubed. 9 times 6 times 16 gives us 864 x squared. 4 times 3 times 64 gives us 768x. And then 1 times 1 times 256 gives us 256. And then for each one of those entries, we just want to add them all together. And so just putting plus signs to connect all of them, we've got 81x to the 4th plus 432x cubed plus 864x squared plus 768x plus 256 as our final answer. And so kind of the next connection that we want to make was, how does Pascal's triangle connect with our combinations formulas? Well, the idea is that the entries in Pascal's triangle really exactly are our combination formulas. So at the very, very top we have a 1. Well, that's the same thing as the number of ways of choosing no things from a collection of no things. So 0 choose 0 is, there's only one way to do that. The number of ways, so for the second row, we've got the number of ways that you choose 0 things from 1 is just 1. The number of ways that you choose 1 thing from 1 is just 1. So we have our entry 1, 1. For our second row, the 1's on the outside, and then the sum of the diagonals above them, so 1 plus 1. Well, that's the same thing as if we had 2 choose 0 on the outside, 2 choose 1, then 2 choose 2. So each row moving across is just the number of things that we're choosing from the row number that we happen to be on. So 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3, 4 choose 0, 4 1, 4 choose 2, 4 choose 3, 4 choose 4, and you can use your calculator to calculate those numbers and see that you do in fact get the exact numbers from Pascal's triangle. Now, the reason for that is that our combination formulas really obey exactly the same geometry pattern that we used whenever we were writing out Pascal's triangle. Namely that if we look at the sum of the two diagonal above it, that it gives us then that number. Now, how does that actually work? Well, kind of what you're seeing here is going through all of those algebraic steps that we start off with n choose k plus n choose k plus 1, and if you want to follow along that you can. It's kind of a little bit of a messy, the algebra is not difficult, but it is a little bit messy as you go through each and every step from the beginning to the very end. But once you get to the very end, you'll see that yes, this actually does give you a binomial coefficient for what would show up in the next row of Pascal's triangle. And so The algebra is there if you want to work through the details. That's great. If you want to kind of save those details for later, maybe after you get a little more experience with algebra, that would be awesome as well. But I wanted to actually show you what all of those steps were so that you would have them for future reference if you needed to go back and work through them later kind of on your own.